Okay, so let's begin. So just by the end of this session, just leave your MATLAB homework on the desk before you leave. I thought we'd talk about one of the guys we looked at yesterday when we were doing the maxes and minimums. And there's this one guy where it was, remember, all points along the x-axis were a critical point, all points along the y-axis were a critical point, and they were all like minimums based on the fact that they were squares. So once you move away from a 0 point, you get a positive number. So I just wanted to show you guys what that would look like. This is the Flailing Butterfly, or I don't know what, as it's affectionately called. Right, so this is actually the guy, this is z equals x squared y squared. So you can see how it looks here. So you notice that one of these guys here is the x-axis. It's not labeled, so I'm not sure, but one of these is like the x-axis and the y-axis. So you can see when you're on those axes, you're 0. You look like a minimum. That's the minimum you get. But as long as you move away from the axes, your thing blows up, right? It starts to become positive. So that's sort of the kind of object that we were looking at. So if you do this, every point along these axes, like here and here, is going to be a critical point. It's going to be a minimum point, which is what we found. And I just wanted to show you guys what it was looking at, because someone asked me after class and what this thing looks like, so I thought it'd be nice to like show you guys in math. I don't know if you can see. Right, so yeah, so that's what the guy looks like. All right, so this is z equals x squared plus y squared, and by what we did yesterday, we know we found all the minimum points here and here. It's actually not strange to have like minimum points being every point along a line, because there are things that we've been drawing before.
Like a cylinder?
Yeah, like a cylinder. Like this guy. That's a familiar guy, right? Here's a parabolic cylinder, right? Now if you were to test this guy, you would also have minimum points all the way along this axis, right? So this is z equals x squared, so it's running along the y-axis. And you'd actually, if you tested this, you'd have minimum points all along here, right? Every point along the y-axis would be a minimum point. So it's actually not that strange of a phenomenon. It was just, the last graph was very hard to imagine. And so I just wanted to point out things like that. So there are a lot of weird things that can happen in 3 dimensions. There are things that, like, if you have a continuous function, right? If we're thinking in 2D, right? And you have, how do I, like if you have 2 isolated minimum points, right, in like 2D, right? You'd expect like the middle to be like
a 7 point. 7 point, like a local.
Yeah, like if you have 2 local minimums. Like a W graph, right? That's sort of how things happen, right? If you have 2 isolated minimums, and the thing is continuous and well-behaving, you'd expect like a maximum to be in the middle of it, right? Turns out in 3 dimensions, intuition like that isn't true. So you'll do problems both in the homework and on tests where you'll see things like, oh, there are 2 minimum points, but there's like no maximum between them, right? There's places where the intuition will fail. So I just want you guys to be aware of that, of the sort of things you should be looking out for. But yeah, I thought it would be nice to show you the Flailing Butterfly.
So for points along a line, it doesn't make a difference if they're on the same level for them to be a minimum?
No. So our definition of minimum means that when you zoom in locally, like points are all
But like
higher.
along if it's a parabola extending along the y-axis or something, the point next to it along the y-axis at like the bottom of the parabola would be less or greater than, right?
It would be equal to.
So that in that dimension it doesn't.
No, because our definition was, you know that this guy is a max if he is greater than or equal to all points around, right? And then it's a min if you are greater than, less than or equal to all points, right? So that equal to tells us that points adjacent to it it could still count as a min, right? So all points are either less than or equal, greater than or equal to, so that's how we got the min. Today we're actually going to continue with absolute max and min. I thought it might be a nice idea to review what this looks like in Calc 2, Calc 1 and 2. So let's say we had to do a problem like find the absolute max or min of y equals x cubed minus x on minus 1 to 2, make something absurd to 10. Okay, so if this was a question back in Calc 2, right, how did we actually do this? Huh? First he found the critical points, that was the first step, right? So first you find critical points. And here the critical points would be what? You find y prime and you get 3x squared minus 4, right? And so you'd have for critical points y prime equals 0 because it's never undefined, it's a parabola, it's a polynomial, and so you get 3x squared is equal to 4, and then so your x would be 2 plus or minus 2 over radical 3. Right? Now, what was the next thing you had to do?
Find the minimum or maximum.
Well, was there something you had to check with these guys?
You have to check to make sure that they're on the interval you're looking at.
You have to make sure that they're first inside the interval that you care about, right? Now, these two are, what's this? 2 over radical 3 is roughly what?
It's like 2 over 1.7, so...
So it's
0.8, 0.9.
Wait, a computer. Just use a computer. It's illustration.
Oh, 1.2.
It's 1.2?
1.17. And extra.
Okay. So you do this and you check the critical points. So obviously one of these guys actually falls outside your window, right? So here you'd only be concerned with the x equals 2 over radical 3, right? Only the positive value you care about, right? Then, so now that you know that was the critical point, what was the next thing you had to do? What was the next thing you have to do for absolute maximum?
take the second derivative.
Do I need to classify that? Right, which means I didn't have to classify this to know if it's a local max or min. I don't really care, right? When you're talking about absolute maxes or mins, you didn't really care. But after you find the critical points, then you have to test the value of the endpoints. So now you're going to test the critical points, which means you're going to have to find y of this guy, 2 over radical 3. You're going to get an answer. Then you're going to test the endpoints. So you find y of minus 1. You find y of 10. Minus 1 and 10 should not be a problem. So y of minus 1 would be minus 1 plus 4. So that's 3. Y of 10 would be 1,000 minus 40, right? Y of this would be roughly what?
root 3 minus 4 minus 8 over root 3.
Yeah, give me somewhere where you can compare it.
Negative 3.8.
Is that right?
He gives a negative number.
No, I put it there.
What did you get? What did you get? Negative 3.08. Okay. Okay. And so your answer to this question would be what? How do you answer the question? Yeah?
That there's a.
So you'd say the absolute
my hand,
max.
guys. I don't know
Absolute max is
10 and 16.
right. Y of 10 equals 960. Right. They usually talk about the value, so you want to get the Y value. And your absolute min is Y of 2 over radical 3. 0.8. Right? Now the point of this was what? When you're talking about absolute max and min, what do you actually care about? You just care about who's the biggest value in some interval and who's the smallest value in some interval, right? You don't care if it's a local max or min, it doesn't even matter. So if you were to graph this guy, what would the graph look like? What would the graph of this look like?
A squiggly.
Yeah, and so it would look like what? Like that?
Yeah. It crosses the x-axis twice.
It definitely has two x-intercepts, right? So what would it look like? Come on.
Down, cross the x-axis, or touch it and then go back up.
No, it has to cross it again.
How do you know? The x-intercepts you have would that be what it looks like?
It crosses at 4 and it crosses
Yeah,
at negative
two students are watching
1.17 and it crosses.
Oh, two students, they can't draw the cube.
It crosses in 3 places.
You guys forgot how to draw graphs?
No,
That's going to be important in
It
like,
crosses.
Factor.
like 2 sections away from this. We're going to need to know how to graph
No,
these things
if
really
you
well.
factor, it's x times x minus 2 times x plus 2. So you have roots at
Exactly,
minus 2
so
and
you
plus
factor
2.
this guy,
Right, it crosses.
right? So you have x times x minus 2 times x plus 2.
Plus 2.
Right, so it crosses in 3 places. So it's 0 minus 2 plus 2. So it's going to look like this. Right here is where it's at 2, 0, minus 2. Right? Now the interval I gave you was from minus 1 to 10, right? Which means I only care about from here, minus 1. Going up to 10. Let's pretend 10 happens here. Right? Which means in this interval, the only things I want to identify are who's the largest value in that interval and who's the smallest value in that interval, right? The smallest value clearly happens here, which is the positive one of the critical points, and the largest value clearly happens here, which is at the end point, right? It's not a local max or min, but it's the biggest guy in the region, and that's all we care about. Very similar in Calc 3, we're sort of going to be doing this. We're going to find all the critical points, but we don't care about classifying them. So we're not going to do the test for D to determine is it a max or min or saddle point. We don't care. We just care who has the biggest Z value, right? And so what we're going to do is we're going to first find the critical points, figure out which one is in the region that we care about. We can test that value. Then we're going to test the endpoints. Now the difference here in 3 dimensions is your endpoints are now boundary curves, right? They're not single points anymore. You're going to be testing how the function behaves on an entire curve. And basically what's going to happen is the problem is going to regress to the Calc 2 situation, and you're going to have to do this, which is why I thought I should remind you guys how to do this. So in Calculus 2, you have that sort of curve. If you have an interval, You find the critical points, make sure you find which ones fall inside the interval, then you test those critical points, then you test the endpoints, see who's the biggest, who's the smallest, right? At the end of the day, right? So now that we've reminded ourselves of that and how to draw a cubic function, let's do this in calculus 3. So we're going to continue with 11.7. Right, so in Calc 2, we were only looking on the intervals. Our boundaries were just points, right? In Calc 3, we're working in several dimensions. We can bound something by an entire curve, an entire region. Right? So that's basically what we're going to look at. So I had to write some notes here. Yeah, so basically my discussion where I said I can skip all of those notes. Okay. So let's actually jump to the summary. Find absolute max. A continuous function f on a closed bounded region 1. You're going to evaluate f at all critical points in the region that you're given to. Find the absolute max min on the boundary which it's basically going to look like Calc 1, and we're going to see how that happens here. Okay. 3. The largest value from 1 or 2 is the absolute max. The smallest or 2 is the absolute. Okay, so it looks simple enough. So let's actually try it. Why is it so hot in here?
He called someone in already.
What?
Something's broken. Mark called about it.
Example, find the absolute max and of
No, B. B is B.
start with that one. What does the region D look like?
Square? Well, it's a rectangle.
It's a rectangle. Right, so this is the x and that's the y. I want the x to go between 0 and 4, y to go between 0 and 5. So D literally describes a rectangle.
Are we in 2 dimensions or 3?
We're in 3 dimensions. This is, I'm looking, so my surface is doing something, right? The surface is doing whatever, blah, 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 right? But I'm projecting, I only care about the region above this rectangle. Right, so I'm looking at, right, so there's a portion of the function here that I'm concerned about. And I want to know who's the biggest value on that piece of the surface, who's the smallest. Right? So this is your z equals f of x, y. Right? So usually if they give you a multivariable function and they describe a region here, they're just talking about the part of the function that's projected over that region. Right? And we're going to talk more about projections today when we get to integration. So this is basically the idea. If I restrict my function to this domain, who's the biggest value, who's the smallest value, right? That's what we want to determine. So what's the first thing to do? We're going to find all the critical points that fall inside that domain, and then we're going to evaluate on the boundary. So let's do that. How do we get the critical points? Fx is here, 4 minus 2x, right? Fy is Fy is, okay, so for critical points, we need 4 minus 2x equal to 0, and we need 6 minus 2y equal to 0. This means I need x to be 2, and I need y to be 3. This means that 2 comma 3 is the only critical point. Right? So f of 2 comma 3. Well, it's 2 comma 3 in our region. First is what we have to check. So 2 would be here, halfway between the 0 and the 4. 3 would be 3/5 of the way between 3 and 5. So the point I'm talking about happens here. So a critical point happens above this point here. So I'm going to test the critical point f of 2 comma 3. Just plug in 2 comma 3 into that, right? So what does that look like? This is 4 times 2 plus 6 times 3 minus 4 minus 3, 6 is 18 minus 13. So that's just 5 plus 8, right? I don't want to box that because I don't know if that's going to be an answer. Right? So we find out the critical points and we evaluate it. Okay. So the value, the z value at that point is 13. I don't care if it's a max or a min because I only care about the value that it's giving me. Okay. So then I move on now, and I'm going to test the boundary. So here's how you test the boundary in a calc203 situation. How many boundaries are we concerned with here? 4. There are actually 4 different boundary curves that we have to worry about. So there's first the boundary curve between 0 and 4, right, I can call D1. There's the one between here to here, that's D2. Here to here, that's D3. Direction doesn't matter, I'm just marking curves. Here I can call this D4. Now we're going to have to test all the boundaries, right? It's sort of like testing the endpoints, except now your endpoints are end curves, or boundary curves that's surrounding this region, right? and you test them one at a time. So let's look at D1. Right? So we're going to test this boundary. Now in D1, what is the curve D1? Give me an equation for the curve D1.
X equals 4.
Huh?
Y equals 0.
Y equals 0. It's a curve running along the x-axis. The x-axis is the line y equals 0. So D1 is actually y equals 0. And what are the limits on this function? Where x goes between 0 and 4. Right? So if I'm above this line, right, what does that function look like? So here, our function is f of x, and the y I replace with 0, right? Because that's what my y values attain on that boundary point, right? So it means I'm going to go to my original function, and everywhere I see y, I replace it with 0, because that's what the curve I'm on. So this is actually 4x minus x squared. And notice that this is now a single variable function, and moreover, you know an interval that you want to test it on. Right? Now it's a calc2 problem. Find the absolute max on this region. That's what I'm going to do. So critical points, this means I take the derivative with respect to x, I get 4 minus 2x, set that equal to 0. This means that x equals 2, which is in that region. So, and so here, test critical points. It means to test f of 2 comma 0, right? That's going to be my critical point, because I know it happens at the x value 2. So the value when x is 2 is going to be what?
4.
Right, it's going to be 8 minus 4.
What does it say there? So here, comma.
Here R, that's O-U-R. Right, so the idea is you have a region, you figure out an equation for it, and you substitute that expression for the equation into the function, right? Then you actually get a function in a single variable. Yeah?
So these weren't vertical or horizontal line segments, but we, I guess, parameterize it, and we're in a single variable thing?
You don't have to parameterize, no.
Not in this case, but like if one of them were, oh, no, obviously.
No, you wouldn't have to. Are you guys with me so far here? So I'm testing this boundary, that's y equals 0. So I go to my function, plug in y equals 0. I get this function, right? So over this line, my function looks like this. I need to find the absolute max and min on that, right? So what I do is I find the critical points. I know for the critical points, x has to be 2, right? Which means I already know the y is 0. So my critical point actually happens here. And so I test the critical point, now I test the endpoints. Now the endpoint is when x is 0. That gives me f of 0, 0. And when x is 4, that gives me f of 4, 0. Right? So I end up on this line testing 3 points. F of 0, 0 is obviously 0. F of 4, 0. Now if I plug in 4 here, I again get 0.
If plugging in y equals 0 had given us multiple solutions for x, then we would have multiple critical points, right?
Right.
Y equals 0.
Yeah. So it's possible to plug in a y value, and here you get a cubic, and you can have several solutions for that. Right? So, huh?
You need to do this for each boundary.
For each boundary, right? So let's continue. So now if we're on D2, let's do D2. What's our function? Huh? No, what's the function? X equals 4, right? and it's bounded on y goes from
0
to 5. So now we're looking at the function 4 comma y. Right? Now 4 comma y looks like what? Plug in 4 for the x's, they'd actually cancel. So I look like 6y minus y squared, where my y value is on 0 to 5. So I first find the critical points. This means I find the derivative with respect to y. Set that equal to 0. This means that my y should be 3. And so test here I'm testing f of 4 comma 3. Which means I can just plug in 3 here. 3 6 is 18 minus 9. Right?
No.
And I get 9. Test endpoints. And this is testing when y is 0. So this is 4 comma 0. Which here is actually going to give you 0. And when y is 5. When 4 comma 5. Which is going to give us what? That's 6 times 5 is 30, minus 25, so it's 5. Right? Someone remember this. Let me write it over here. Now you do D3. What does D3 look like? It's y equals 5, where your x goes from 0 to 4. So here you would have f of x comma 5. So you plug in 5 for this. That just gives you 5. This is 4x minus x squared plus 5. Find critical points. This means you take x 5 is 4 minus 2x equal to 0. X is equal to 2. So test critical points. And we have f of 2 comma 5 is what we want to test. So I just plug in 2 here. That gives me 8 minus 4, so that gives me 9 as well. Test endpoints, which means I want to actually plug in x equals 0, 0 comma 5, which will give me 5, and x equals 4, 4 comma 5, which we already found. 4. On B4, we know that our x equal to 0, right? So here we have f of 0 comma y is going to give us a function. That's just going to be 6y minus y squared. Find critical points. This means derivative with respect to y is going to be 6 minus 2y equal to 0. This means that your y is equal to 3. So you test critical point. This means you're testing f of 0 comma 3. Which means you plug in 3 here. You get 9. Test endpoint. So this was actually y goes from 0 to 5. So we can test 0 comma 0, which is 0, and we can test 0 comma 5, which is what, 5? Therefore.
Javon?
Yep.
The camera won't get that.
Oh, they can. Okay. And we had f of 2, 3 equals 13. So then finally your answer would be what? Absolute max is... So all the values that we got, we have to look at all the values that we got, right? We got 4, 0, 0, 9, 0, 5, 13, 9, 0, 5. 13 is the biggest one. So absolute max is f of 2, comma 3, which is 13. What's the absolute min? All right, so we look at the smallest values we got, which was actually 0, right? So the absolute min is f of 0, 0 gave us 0. F of 4, 0 gave us 0. And that was it. Any questions?
Yes, is there any more efficient way of doing this? One of them calc203 tricks?
Not really. There are going to be cases where if they describe your region as a circle, then you can maybe switch to polar coordinates, and sometimes that can take some of the work away. But other than that, not really. It's sort of, you have to find all the critical points and test the boundaries, just as before. So in this case, that would be an answer. I mean, typically you wouldn't get like 4 boundary curves to test. I just did this for emphasis, like, you know, you have to go through each thing. So if we can do another example. Oh, well, this one I also did a rectangle.
Thanks.
This one I gave 8 boundary curves.
You can probably do another kind of example.
You all think this is pretty good.
I mean, let's look at an example that you might get that's not like a rectangle. I don't know why I picked 2 rectangles. Let's try that. What's going on? You could get a triangle, sure. Ah, that's another rectangle. So yeah, you see a rectangle is possible. They could ask you. I'd probably do it. They're all absolute maximum min problems. Okay, here's one. Let's look at number 8 here.
What is
This is spring 2008, problem 8. Find the absolute minimum and absolute maximum of that function. This is a pretty easy function. On the region y equals x squared. Why did it take it so easy on me?
I feel like if we actually
Example, this comes from, I said spring 08. Was it 08 I said?
Yeah.
So the function was f of x y equals
y minus 6x minus 10?
on the region
Y equals x squared. Then y equals 60.
Okay, so basically here, in this case, what our boundary curves look like is a parabola for part of it, and then there's a straight line for the other part, right? So you have y equals 16, and you have y equals x squared. So this, our boundary region here is this D, right? So you see here, you only have 2 curves to test, right? But you have to test all the curves. So first what we're going to do is we're going to find the critical points. What do you need to do? You need to find partial with respect to x, right? In this case, it's just minus 6. Partial with respect to y, in this case, is 1. These are never 0, so no critical point. Right? So your partials here gave you answers that could never be 0, so there is no critical point, right? It's never 0 or undefined. So you just move on, test the boundaries. Test boundaries. So here my boundary has 2 of them. Okay, so I'm looking at y equals x squared on what's the boundary?
Plus minus.
It's go between plus and minus 4, right? So in this region, take f of, instead of y, we're going to put x squared, right? And what does our function look like in that case? It's going to look like x squared minus 6x minus 10 on the interval minus 4 to 4. So now you find the critical points. This means you need 2x minus 6 equal to 0, which means x equals 3. So now you test the critical point. So the critical point happens when x is 3, right? So this is going to give us f at what value? 3, 9. Right? It's 3, 9 in our region.
Wait, did you just write there there's no critical points?
Right, there's no critical points.
So what are you testing here?
Boundary.
Oh, the boundaries.
Right. So there's always 2 things to test when you're doing an absolute maximum min problem, right? You test where the critical points are and you test on the boundary. So here there were no critical points to test, so I just move on to the boundary.
So the boundaries are critical points?
No, on the boundary, my function looks like this, and this has critical points.
Okay.
Right. It's not critical points of the function as a whole. It's just critical points if I'm concentrating on the boundary. Right?
Why do you have 9?
Because
Because y is x squared. Right. So when whatever my x is, I have to square to get the y. So I have a 3 comma 9. So what I do is I go here and I plug in 3. Right. So that's going to be 9 minus 3, 6 is 18 minus 10. So that's what? Minus 19? Test boundaries. Now the boundary is going to be when x is minus 4. So it's going to be minus 4 comma 16. And then I'm going to test f is positive 4 comma 16. So if I go here and plug in x equals minus 4, what do I get? I get 16 plus 6 plus 24 minus 10. Right? That gives me what? 30. And then if I plug in positive 4, I would get 16 minus 24 minus 10. What is that? Minus 18. Now I test the boundary y equals 16 on, again, x goes from minus 4 to 4. Now here my function is x comma 16. So I just go to my function over there and I plug in y equals 16. So I would have 16 minus 6x minus 10. Critical points. This happens partially with respect to x is minus 6, so here I have no critical point. Test boundary. F of x can be minus 4 comma 16, or x can be 4 comma 16. And we already found these. This was 30, this was minus 18. Therefore, absolute max. Alright, so the absolute max is the biggest value, which here is this guy. Absolute min is the other guy. Question?
actually, yeah.
Yeah?
Shouldn't the absolute minimum be at 3.9?
Oh, yeah.
Because that's negative 19.
I forgot that. Yeah. Right, that's smaller than minus 18. So we had 19, we had 18, we had 30. Right, so we picked the biggest of these values and the smallest of those values. And so 30 was the biggest, minus 19 was the smallest.
Test boundary, is that the same as test the endpoints down here?
Yeah, test boundaries is sort of what you call it in calc2. Yeah. I wanted to emphasize when we're testing points as opposed to boundaries. So here, this is a boundary. But the boundary itself has endpoints. That's sort of how you do it. We'll stop there, take a 10-minute break, go through that.